Howdy, and welcome to a short little video about lab number 4 for MEEN 410 students. Okay, so first of all, I discovered a cool new little feature on my iPad where I can do things like this, which is pretty exciting, as opposed to needing to write red ink all over the lab handout every time. Anyway, that aside, one thing I want to real quickly draw your attention to is that if you are not in MEEN 410, this is the wrong handout for you. Okay, so MEEN 410 students have a different handout than MEEN 611 students. So make sure that if you're using this handout, that you are in fact in MEEN 410. If you're in MEEN 611, I've got a video for you too, and you'll be able to watch that video with the correct handout. Okay, so lab number 4 is basically having you study the behavior of a natural gas spark-ignited engine with changes in ignition timing. Okay, and so the way that we'll be varying that ignition timing is by changing the spark timing of the engine. And so you'll be looking at data that was collected on a large bore single-cylinder engine that's operated at several different spark timings and 2 different engine speeds. And you'll be analyzing that data for crank angle resolved cylinder pressure, which is given to you, brake torque, which is given to you, indicated torque, which you'll need to calculate, indicated mean effective pressure, which you'll need to calculate, combustion duration, which you'll need to calculate, and ignition delay, which you'll need to calculate, and then finally brake fuel conversion efficiency, which you'll need to calculate. Okay, so if you're watching this video, then you will have already sent me your team preferences, but I included that in the lab handout, thinking I would have been able to release this to you sooner than when I had, but I've just included it here for good measure. Okay, so the main independent parameters that you're going to look at, that is the control parameters, in other words, the things that we purposefully changed, right, as opposed to an observed parameter, are ignition timing, or more specifically spark timing, and engine speed. Okay, so half the data are collected with the engine running at 525 RPM. The other half of the data are collected at 475 RPM. For all of the data, the throttle position, which is controlling the fuel flow rate, is set constant for each speed condition. In other words, there's a fixed throttle position for 525 RPM, and there's a fixed throttle position for 475 RPM. So what that tells you is that the same amount of fuel is being delivered each cycle for each speed as we change spark timing. Okay, so if you're looking at spark timing data and you're trying to explain a trend as to why torque changes as spark timing changes, and you argue that it's because the amount of fuel that's being delivered is changing, that's incorrect. Okay, the engine is using the same amount of fuel every cycle for every spark timing of the engine. Okay, so the data, as I mentioned, they're provided to you in a spreadsheet that's available on Canvas. I have a little video that'll take you through that lab data, and you use the same data. Both 410 and 611 students use the same data, and so there'll just be one data file located on Canvas. You provide some description of how to interpret that data in the spreadsheet, but I'll refer you to that lab video for more complete data or more complete information on that. There is data at the end of this handout, table number 1, that you're also going to need to use, so I'm just very quickly going to jump to that. So you can see that table of data listed here, table 1, and so you're provided, for example, the brake horsepower, the rated RPM, the rated speed of the engine, the bore and the stroke, the displacement, the volume displacement for the engine. And note that it's a single-cylinder engine, and so that displacement corresponds to just one cylinder. As I explained in the lab data video, this is a single-cylinder, large-bore natural gas engine that is used to operate pump jacks in various oil fields, oil and gas fields. And so you don't necessarily need a lot of power, you just need a lot of torque. And so that definitely is what's provided by this single-cylinder engine. You're also given the clearance volume, and so with these two pieces of information, you're able to determine various parameters that you need to know. The BMEP is provided for you. This would be the rated BMEP, the rated brake mean effective pressure, corresponding to that rated brake horsepower. The compression ratio is provided. The peak torque at the rated condition is given. Now, the two critical pieces of information that you'll need to know from this table is the gas meter pressure and the gas meter temperature, and the time that it takes to ingest 10 cubic feet of natural gas at rated load, okay? And so you'll use these three pieces of information to determine the mass flow rate of the fuel, which you'll then be able to determine the mass of fuel per cycle. And that's going to help you determine your brake fuel conversion efficiency, which is one of the pieces of analysis that you need to do in the lab. Okay, so you're going to generate several plots that correspond to four major pieces of information. There'll be more than four plots, just to be clear, but there's four major pieces of information that you'll be looking at. The first is in-cylinder pressure, okay? So you'll be plotting in-cylinder pressure as a function of crank angle for each spark timing, okay? Plotted for the two engine speeds, okay? So what I want is I want two plots, one plot for each speed, and on each plot, you're going to have several pressure versus crank angle curves corresponding to the different spark timings, okay? So when you go to the lab data video, you'll find out that there's 5 spark timings for each engine speed. So that means that on one of these plots, say at 525 RPM, I want 5 curves that correspond to the 5 different spark timings, pressure versus crank angle. And then you'll create a second plot for 475 RPM where you plot pressure as a function of crank angle for the 5 different spark timings. So 5 curves corresponding to each spark timing on each plot. You'll also plot brake torque and indicated torque, both of them on the same plot using the primary y-axis of that plot. And then on the same plot, indicated mean effective pressure, IMEP, plotted on the secondary y-axis as a function of spark timing for each speed. Okay, so you're going to create 2 plots, one plot for each speed, okay, where you're plotting brake torque, indicated torque, and IMEP as a function of spark timing, 2 different plots for each speed, okay? The third item that you'll plot is combustion duration and ignition delay as functions of ignition timing for the 2 cases, the 2 speed cases. So again, 2 plots, I don't say that here, but you'll be making 2 plots, right? One plot for each speed. Okay, and you can, in the handout here provides you some description as to how you can define ignition delay, right? So ignition delay is defined as the time between spark timing and 10% mass fraction burned. Then you'll also plot combustion duration. So combustion duration is, of course, the time between 10% mass fraction burned and 90% mass fraction burned. And those, as you'll learn in the Lab 4 data video, those 2 pieces of information are given to you in the spreadsheet, and you will just need to calculate the ignition delay as well as the combustion duration. Okay, and then the final item to plot is the brake fuel conversion efficiency as a function of spark timing, ignition timing, at just one speed, the 525 RPM speed case. And the reason why we're only doing it at that one speed is because that's the only case that you have fuel flow rate data for, right? So you have fuel flow rate data for 525 RPM, and so that's the only case that you can plot the brake fuel conversion efficiency for, okay? And so you'll be plotting that as a function of ignition timing. And there's this little hint here, of course, tells you how to determine that fuel flow rate based on the data that's given to you in Table 1, as I've already described. Make sure that you use appropriate axes when you're plotting your data. You want to be able to have the axes scaled accordingly so that you are showing the trends in the data, right? So, for example, if you're plotting torque, you want to find what the minimum torque is, the maximum torque, and set that as your min and max for the y-axis so that you can see the trends very clearly in that data plot. Okay. Now, the other thing that's related to this is when you're plotting two different speeds, for example, of the same data, right? So, for example, you're plotting brake torque, indicated torque, and IMEP on one plot for 525 RPM, and then you're plotting the same stuff, brake torque, indicated torque, and IMEP on a second plot for 475 RPM, you want to make sure that you use the same axes for both speeds. If you change the axes and you go to look at the differences between the two, it's going to get a little bit confusing because you're going to require your brain to have to recognize that the values on the y-axis are changing. And so when you do that visual comparison, it's going to be more difficult to do that comparison. Whereas if you make the axis values the same for both plots, for both 525 and 475 RPM, it's much easier to do that comparison. Okay, and so that's just one example. You'll want to do that with any time that you are plotting the same parameters for the two different speeds, right? Like the combustion duration and ignition delay. Okay. All right. Once you have all your plots made, then you just need to get into writing your report. There's some language down here, right, that you want to write your report as a typical lab report. You want it to be typed. You want it to be have professionally acceptable margins and font sizes, which I usually take to mean 1 inch all around margins and type size font 12, just to make it easier for me to read. And again, as usual, there is no page limit, right? But you need to make sure that your discussion is concise and focused. And excessively long reports are going to result in a lower grade, right? Especially if I feel like there's a lot of redundancy or inapplicable text that's being provided in the write-up, okay? Generally speaking, Lab 4 is somewhere between, the written Lab 4 is somewhere between 8 to 10 pages, okay? Again, if it's a little bit less than 8 pages, you don't need to panic. If it's a little bit more than 10 pages, you don't need to panic. But if you give me a 4-page report, that's probably going to be deficient, right? And if you give me a 20-page report, you might be bringing in a lot of extra extraneous items that aren't relevant to the lab. Okay, so this is a guideline, right? It's just a guideline. Ultimately, what you really want to follow through on is to make sure that the discussion is concise and focused, okay? And if you're able to do that, then you should be hitting all of the metrics for a successful grade submission. Okay, so using the plots that you've generated, doing your analysis and discussion, you first want to focus your report on describing the behavior of cylinder pressure as a function of crank angle, as both engine speed and spark timing change, okay? To help you with your analysis, I've provided some questions for you to think about, right? So one question to ask yourself, to ask yourselves among your teammates is, does cylinder pressure vary as expected with spark timing, okay? In other words, are you seeing the expected trends in cylinder pressure among the 5 spark timings for a given speed, right? Why or why not? Make sure that you explain if you are seeing the trends, explain why. If you're not seeing the trends, explain why not. Likewise, does engine speed affect in cylinder pressure, right? Does it affect it as expected? And again, why or why not? You then want to shift your attention to analyzing brake torque, indicated torque, and IMEP as functions of spark timing for each speed, okay? And again, when you formulate your discussion, you want to think about these questions, okay? How do brake torque, indicated torque, and IMEP relate to each other, if at all? Okay, in other words, does brake torque change as you would expect based on how indicated torque is changing? Does IMEP change based on how you would expect it to, based on how indicated torque is changing? Okay, how close are brake torque and indicated torque to each other, right? What is the difference between brake torque and indicated torque? And would that factor be affected by spark timing? Okay. How does spark timing affect torque, right? In other words, are you observing the trend of torque versus spark timing that you would expect based on what we've discussed in lecture? Does maximum brake torque occur at the spark timing that you expect, right? Do your observations from cylinder pressure support where you would expect that MBT to occur, or how torque changes as spark timing changes? Then shifting your attention, you want to discuss the influence of speed, right? Are there differences in the observed torques and IMEP between the two speeds, okay? And if there are differences, how do you explain such differences, okay? Then you want to shift your attention to describing ignition delay and combustion duration with respect to each other, as well as with respect to spark timing, okay? And again, I give you some questions to think about. Do ignition delay, combustion duration, and spark timing relate to each other as you would have expected, right? How do you explain differences between what you expected and what you observe, right? So we'll be talking about ignition delay, combustion duration, and spark timing in class. Are you seeing the same thing in Lab 4 data, or are you seeing something different? And if you're seeing something different, why are you seeing something different, right? If you're seeing something the same, why is there a relationship among spark timing, ignition delay, and combustion duration? What are those things that we talked about in class that are also seemingly appearing in your Lab 4 data? And then finally, you want your lab report to talk about the brake fuel conversion efficiency. And again, you're only going to do this for 525 RPM as spark timing is changed, as spark timing is swept. Okay, and then again, I give you some things to think about to help formulate your discussion. Does efficiency vary with spark timing in a way that you would have expected? Explain why or why not. What would happen in the context of efficiency and NOx emissions if you were to advance your spark timing beyond 21 degrees before top dead center, right? Would efficiency go up or go down? Would NOx emissions go up or go down? Why or why not? And then also same analysis, if you were to retard your spark timing from 1 degree before top dead center, right? Would efficiency go up or down if you retarded spark timing from 1 degree before top dead center? Would NOx emissions go up or down if you were to do that spark timing retard from 1 degree before top dead center, okay? Okay, so that's it. If you're able to capture all of that analysis, then you all are going to do really well on your lab number 4. Okay, and of course, if you have any questions, please feel free to reach out to myself or Kyle. Have fun with the lab. I think this is the capstone of the course, right? And so I hope that you enjoy it and find it a meaningful exercise. Take care. Have a good day.